Hello everyone and welcome to this tutorial. In this tutorial I'm going to show you how to model a simple structure in Abaqus using beam elements, and also show you how to insert prescribed displacements and or rotations, and also play a little bit with the output. So just quickly having a look at the structure we're going to model. It's a 2D structure, as you can see. The nodes are numbered as shown, 1, 2, 3, 4 and 5. Also elements are numbered 1, 2, 3 and 4. And supports are at node, fixed supports are at node 1 and 5, with the spring attached to node 4. They also show the section we are going to be working with its defined material properties, and also some line load applied on element 1, and also a point load on node 3. So yeah, the dimensions and everything is given here. This is to be modeled using beam elements, and in this problem I would like to use the elements as defined here, as opposed to meshing them into sub-elements. It just makes interpreting the results a bit simpler, and also just illustrates how how one can use meshes to have single elements between nodes, as opposed to 10 or 20 or how many you want. Okay, so let's get started. Go to Abaqus, create a new part. As per usual, we call this part frame. It is a 2D planar model space, as we showed, and also a wire element. The approximate size I'm going to be using in standard SI units, so it's meters, newtons and pascals. If I look at my structure, it is 8 meters by 4 and a bit, so let's say 8 by 6 meters. So let's stick with 50 because we can. So say continue, and now we can draw a thing. One thing I haven't really showed is in my previous videos is how to draw with construction lines. So I'm going to try and put some effort into that for a change. So usually I'll go with the shortcuts, but just to show you the other options of using the menu bar. So you go to add and you can say construction. I'm going to start with the horizontal line at the origin. Okay, now I have a horizontal construction line. I press escape. Now I'm going to add another construction line, a vertical one. Okay, so now we have our origin in terms of construction lines. Now having a look in terms of the vertical differences, so it's a 3 meter difference between the first vertical element to node 3, and then another 3 meters, and then 2 meters. An easy way to do that in Abaqus, seeing as I have my vertical construction line, is in add you can go to linear pattern and ask you to select the entities. I want to pattern this line, and in direction 1, which is your x direction, I would like 3, so there's my 3 meters and 3 meters. So if I make the spacing 3 meters, and my direction 2, since it's a construction line, I can just keep as 1 because it doesn't really make a difference. Okay, so that'll be 3 meters offsets. Can say okay, and I need another 2 meters if I look at this thing to get to node 5. So let's create another linear pattern for the last line, and we say okay, make it 2, and the spacing is 2 meters, make that 1, and we say okay. Now the horizontal difference is from the start of my first node to the second node is 4 meters. So let's give another offset or linear pattern for that line. So okay, so now we're looking at direction 2. So in direction 1 is going to be 1, and direction 2 we are making 2, and the offset is 4 meters. And we say okay. Okay, so now the bulk layout is created. Now the only thing we still need is our 30-degree angle that is given there. Now instead of, as opposed to doing some trigonometry to figure it out, we can also add a construction line at an angle. So they ask us for the angle, we just make it 30 degrees and snap it to our top node over there, and then we do the same thing and just make it minus 30 degrees for the other line, which is technically not necessary if you already have that line, but okay. Let's put our other 30 degrees there, And there's all our construction lines. So now we can just go on and draw our little structure. So from that node 1 to node 2 to node 3, node 4, and node 5 sits over there. And that's it. So we say done. There's our little outline. Okay, so now our part has been created. We can continue creating our material. Just double click on material, give it a name. Let's give it a name, it's steel, seeing as typical steel section. Density is not really required. I'm just going to go with elastic material, and our Young's modulus given in the problem is 200 gigapascals, so I'm going to make it 200 E9, which is for giga. It's sticking to my SI units, and the Poisson ratio is 0.3. Excuse me, and that is about it. Okay, so the material is defined. Next, we need to define our section. Click on the section. It's a beam section. We make it a beam. Just make it our I section. Maybe give it a nice name. Okay, so you continue. Beam, we need a profile, so we create a new profile. It's an I shaped. So make the profile I profile. So continue. Now it gives us options to enter our eye profile. Just looking at the dimensions again from the drawing, it is 200 wide and 300 long, and the thing says the flanges and the web are each 10 millimeters thick. Okay, so it says our L, or which is the height to the centroid, is height over 2 in our case, so that is going to be 150 mils, so let's make it 0.15. Height 0.3 meters, 0.3 B1, 0.2 B2, 0.2. All our thicknesses are 10 mils, so 0.01, 0.01, and T3 is 0.01. Okay, there's all our dimensions entered, so we can say OK. And the material is automatically selected, seeing as we only have one material at this stage, and we click OK. And now we need to assign the sections and profiles we just created. So we go expand our part, and there you can see section assignments. Select the regions. I'm going to define my whole structure as a set, so let's make it structure. Just give it a name, and we need to select all of our elements and say done. And our section is the I section we just created. So OK. And that's it, so we can just type escape or click the X. Section assignment has been done. The one thing if you working with beam elements, you need to assign orientation to your beams. There's where this assign beam orientation button comes in. So we can select our sets. So we just created the whole structure, so we go to sets and say structure. And we say continue, then it assigns it to our whole structure. Just select the default value, and that looks okay to me, and we say OK then, and dismiss, seeing as we don't need to do another section assignment. Okay, and that is our section assignments done, as well as the orientations. Next we go to meshing. If we go down the line, we can also add our spring at this stage, so expand engineering features, double click on springs. You can also right click and say create, depending on what you like. Just going to go say spring, and we're going to connect points to ground. What you could have done is you could have made another node, made it 6 and made it a distance and give it a fixed support. But seeing as we are not really interested at this stage as in the reaction of the force there, we don't really need to expand our problem to accommodate that. So we're just going to add the spring at node 4. Okay, so I'm just going to say connect points to ground, as it doesn't make a difference where the spring is actually connected. So connect or continue, and it will ask us where we want the spring. So that node over there, and then it asks us for the spring stiffness. Degree of freedom is the first thing. Our spring is in degree of freedom 2. You'll notice the numbers are 1, 2, and 6, which is for a 2D beam element. If you think in a 3-dimensional beam element, you have 6 degrees of freedom per node. So it is your force in X direction, force in Y direction, In a 3D beam, your degree of freedom 3 would be the force, shear force in the Z direction, and then the 4, 5, and 6 would be the moments about each axis. So in for a 2D problem, you only have force in X, force in Y, and rotation around Z, which is 6. Okay, and since our spring is in the vertical direction, we are going to say degree of freedom 2. And the stiffness, since we work in Newton meters, it's just the right unit, so you can just say 4 times 10 to the power of 6. So you can just type 4e6. So okay, and there's our little spring over there. Okay, now we move to meshing the structure. So double click on mesh and the menu change. As I've said previously, we would like to use the elements as defined here. So how do you mesh that? The simplest option is to just make your seed size bigger than the element, or the longest element, then it can't divide it into sub-elements. So just show you how that's done. So you can say seed part, and by default it takes the element and try to divide it by 10. We are just going to make it, let's say, 5 meters, which is longer than our longest element. So apply, and we check the seeds. All our nodes are at seed points, so that is what we want. Say OK. Then mesh, just to check the element types for. I can select all our things, all our elements, and see for beam elements we can have a linear or a quadratic type beam element, and the element name being displayed a 2-node linear beam element in a plane, or a 3-node quadratic beam element. In our case, I'm going to stick to the linear one. I just wanted to show you how you can actually change that. Okay, I'm going to click OK. Now we're going to mesh our part, and just say yes. And now you can see everything is turned blue, so we are good to go on that front. Okay, so now the part is defined with all the elements, the meshes, the sections, all those things. Now we can continue to the assembly. So you double click on instances, and create it from our frame, and just say OK. Our instance is there. Now we can continue to apply loads. So we create a step called our load step, also a static general step type. So continue, don't worry about the description at this stage. Okay, now we can apply our boundary conditions in the initial step. So you would say boundary conditions, just say supports. You don't have to change the name if you don't want to, but always nice to have proper naming in place. So we can either go to a displacement rotation boundary condition, or if you know everything is going to be fixed, you can use incast ray as a shortcut. So I'm going to go with a shortcut and select my nodes. We have a support over there and a support down there. And now to select multiple nodes or elements in Abaqus, you just need to press and hold the shift key. And I'm going to say done. I'm not going to create a new set in this stage. And as you can see, incast ray says all displacements and rotations set to 0. So we say okay, that's what we want, and our supports are shown. Now applying our loads. Expand our load step and double click on loads. I'm going to start with the 100 kilonewton point load up there. So I'm going to say it's a concentrated force. I'm going to name it point load. It's a load step, and say continue. Select points, it's going to be up there. We say done. And in the X direction we have 0, in the Y direction we have minus 100 kilonewtons, so it's a minus 100 times 1000. Say OK, and there's our load applied. The next load is a line load, so shown as there, and the slope of that line is going to be 10 over 4, which is 2.5. And it's applied in our X direction on that element. So let's apply that as needed. So we create a new load in our load step, and this is going to be a line load. So continue, and I'll select the bodies. I'm only going to select that element, seeing as the only one that's getting the load. And now it wants the distribution, seeing as it's not a constant load, we need to create another one by creating an analytical field. So you're going to make an expression field, analytical field 1, just say load field, say continue. Okay, so now I'm not going to define another coordinate system, seeing as this thing is actually correctly already on the origin there and vertical. So instead of saying 2.5 x, which would be a vertical load, to make it horizontal we just say 2.5 times y. So we're just swapping our coordinate system around. Okay, and that's about it. 2.5 times y, so we say okay. And component 1, which is component in the x direction, I think we should say 0. And as seeing as we technically said 2.5, it should actually be 2,500. So I'm just going to make the component 10,000 or 1,000. Then it should be okay. So make it 1,000 there. We say okay. And you see I did it wrong. So how to edit it, you go to our load 2, which should technically rename, but that's okay. So you make our component 1 1,000 and component 2 0, and see if the direction is correctly now. Okay, that is what we want, but it seems a bit uniform, so let's just edit it again and see. Oh, I must select my load field I created, so that should be a bit better now. Okay, now that is what I want. Okay, so now the loading is applied. We are not going to show load cases or do load cases in this specific example. So to get moments out of your, or moments and shear forces out of a beam element analysis, you have to edit the field output and just request that it also gives you the nodal forces in beam section orientation. And our reaction forces and all those things should be selected automatically. Reaction forces and moments, so that's what we want. The moments, element moments, okay. So that seems that we have everything we need there, and I think we are all set. Next you create a job, just make it, well, job 1 is fine in this case. So continue, you don't need a description, and we submit it, hopefully there's no mistakes. While it's submitted and running, give it a moment. It's completed, which is good news. If there's errors, you can see what its status is, or what the difference or the error was, and you can try and fix it. Usually it has to do with forgetting to mesh it or meshing it wrong or something similar, or yeah, see what the error is and try and resolve it from there. Okay, so now since this thing has ran, we can go to results and see if everything was as expected. Just click on the contours. Okay, one thing you'll notice, I changed my output settings. So how you get the stresses to show like that, you click on this button over here with the contour options. You say banded and it showed tick marks for line element. If you just say line, you get the normal, remove the tick marks, you see this. So the standard one I think is banded, and if you just say show tick marks for line elements, you get these little distributions, which is quite nice. So if you want to see our shear force diagram, which is 1 is axial, 2 is shear, and there's our shear force diagram for this structure. Moment diagram, there we go. It is linear because we only have nodes at our endpoints. If you want the proper moment diagram due to the distributed load, you'll need to provide or divide these elements into sub-elements. Then you'll get the proper moment diagram. But I'll show you that in a moment when we get there. Okay, so this is about it. To increase the text of this little block, you go to viewport, viewport annotation options. You go to legend, and you can click set font. So instead of 8 we say 12, just make it a little bit bigger. And there are values are nice and large. Okay, so this is what I wanted to show you up until this point. Now I'm going to go back to my model and add some prescribed rotation at that node over there. And so yeah, let's have a crack at that and see how it's done. Okay, so you go to model. The prescribed displacement is going to be, or prescribed rotation is going to be a boundary condition. So we can go to our initial step and add a boundary condition over there, and just name it BC2 displacement rotation. Say continue. I want to go to that node. You say OK, and now you'll see we only get the option to fix it or not. So this just indicates we are in the wrong step. So if you want to use prescribed displacements or rotations, don't do it in the initial step. Rather go to your load step and add the boundary condition there. So same thing as before. So we're going to name it prescribed rotation. Say continue, select our node again, say done, and now we can say, okay, I want a 1 radians rotation at that node. If you have a prescribed displacement, you just select those and enter the required displacement over there. In this case, I'm just going to say there's a rotation prescribed and say OK. Another thing I'm going to do, I'm going to remove the spring. If you don't want to delete it, you can rather just use the suppress option, which effectively removes it, but it makes it a lot easier to just reactivate it in your model, as opposed to deleting it and reinserting it again from the start. Okay, so that is the only change I wanted to make. So now I'm going to rerun my job, resubmit it, and say okay, that's fine. I'm quickly going to take a sip of coffee while we wait for this thing to run. It takes a while, but it gets the job done. Now it's completed. I'm going to say results again. Click on that little button over there. And now we change it to shear force, bending moment. Okay, looks a little different than it did previously, which is a good sign. Okay, now a few things I actually wanted to show with regards to output. In the case that you want tabulated results, as opposed to just reading guessing the numbers from here, you can go to, a nice way you can do it is going to report. So you report field output, and you select unique nodal, and you say what you actually want to be reported. So I'm going to select my beam forces as well as my reaction forces and reaction moments. You can also report the displacements if you want. There's a lot of options depending on what outputs you have. And in terms of setup, I'm just going to name my report file frame.rpt, and output format single table. You can use separate tables if you want, and you can play a little bit around with the options given here and see what actually pops up. So when you're done with that, also if you just want to add to a different results, so for example if I wanted to do it with or without the displacements, I could just append to the file. So for argument's sake, I'm going to show you how to do it. So I'm going to create a new file, so not clicking append, I'm going to apply it. So the first set of results are going to be with the prescribed displacement, or sorry, prescribed rotation at that node, and then I'm going to go back to my initial model, and in this case I'm also going to suppress my prescribed rotation, and I should go, apparently I can't suppress it, which is interesting. Let's see if I can suppress it from here. Yes, there you can suppress it down there. So you can't suppress it in the node step specifically, but if you scroll down you can suppress it in your prescribed rotation. So I'm going to reactivate my spring, Because I say resume. Now the spring is reintroduced. Rerun the job. Wait a few seconds. Maybe go for a quick sip of coffee. And click to results. And now we're going to go to report again. Say field output. Same thing should still be selected, unique nodal. And now we're going to append to the file so we can see the difference that the rotation makes. So you're just going to say apply. And now it shows you where the file are. This file should be in your working folder. In my case it's in my temp folder. So you go to frame.rpt and we say edit with notepad. And the whole report is nice here in tabular format. So this is the first table is with the prescribed rotation, and the second table is with the spring and without the prescribed rotation. You'll see the numbers actually do differ, so there was some difference. A nice thing you can do if you want to make a little report from these numbers, you can, and you have access to Microsoft Excel, you can just select all of them, Control C for copy, go to Excel. I'm going to make a heading saying prescribed rotation. Paste it in there, and Excel has under the data field you have the text to columns option. So you just say fixed width and say next, and it also auto detects where the columns start and end. So when you're happy with that, you can just click finish, and then all of the cells are in the same column, so that's quite nice. Okay, so now where the prescribed rotation is, I'm going to say, just copy that over there, copy, paste, yay. Okay, and say spring applied or whatever. Okay, now I'm going to do the exercise again. So I'm going to go to the second table, say copy, paste, select the rows you want to use the text to columns thing, fixed width, next, and finish. Now all is beautiful. If you want to create graphs from this, plotting changes of the difference, you are more than welcome to do so. One thing you'll notice in Excel, for example, let's say I want to add a value to that last one, so I'm going to say that value plus 5, for example. I'm going to get an error. The reason for that is because you'll notice in Excel, if I say equals 13.5 or 3, it uses a comma to separate decimals, and in this case it uses periods. One simple way to remove this or solve this is to select everything, just say Control F for find and replace, and you can replace the periods with commas and say replace all, and now we can actually add 1 to our value. So that's actually a nice way to adapt it. Okay, so that's how you can create a nice little tabular output of your reactions and element forces. Another nice thing you can do is if you want to, for example, plot or submit the shear force and bending moment diagrams, you can select the shear force from here. You go to plugins, tools, and say save current viewport, and just give it a name and say bending moment diagram, and we say save, and you say it's saved in additional images. So if you go to our temp folder, additional images, there sits bending moment diagram. So you can literally copy that image and go to your Word document and say paste it right there. So there's a nice image showing our bending moment diagram. Okay, yeah, that's about it I wanted to show in terms of that. One thing, if you want to, as I've said, better looking moment diagram, you just have to go back to your model, go to your meshing, and we say seed part, and instead of 5 we say 0.4. Say apply, delete the meshes that are there, and we say mesh part, we say OK. Now the meshes are a lot finer, so we should get a lot more accurate moment diagram out of this model now. Okay, the job is running. Just showing the results. See, now there's a lot more lines, which is a good sign. And there's the bending moment diagram, nicely curved, showing the results. So yeah, that is what I wanted to show in this video. Thank you very much for watching. If you enjoyed the video, please like it and share if you think it can help anybody else. And subscribe to my channel for more videos like this. Thank you very much.